Ladies and gentlemen, it's my pleasure and honor to introduce the person who needs this introduction of all of us. Carlo. He's no introduction, so I'll say only two brief things. He is, of course, the author of many books and articles in Italian and English and I don't know what other languages. He's also a maverick, which I like very much. Maverick.
Well, I'm afraid I will not speak about such trendy things. I'm afraid I will not speak about such trendy things as economics, policy of science, sociology of science, but only about poor old philosophy. My talk is about towards a logical discovery, not about towards the logical discovery. This is not a new subject. It was, well, in the ancient world, Aristotle, of course, was concerned with it. And in modern times, Bacon, Descartes, and other people. Anyway, in the 17th century, can you hear me?
Yeah.
Yes? Okay. In the 17th century, it was widely felt that the then current logic paradigm, scholastic logic, was inadequate to the needs of the new science. I say scholastic logic because it was not really Aristotelic logic, but it was the interpretation of Aristotelic logic by scholastic logic. For example, Bacon stated, scholastic logic is useless for the discovery of sciences. It is good rather for establishing and fixing errors, which are themselves based on vulgar notions, than for inquiring into truth. Hence, logic is more harmful than useful. Similarly, Descartes stated, scholastic logic contributes nothing whatsoever to the knowledge of truth. It does not teach the method by which something has been discovered. Therefore, it is entirely useless for those who wish to investigate the truth of things similar to Bacon. The dissatisfaction with scholastic logic gave rise to several attempts to develop logics of discovery, alternative to scholastic logic. The resulting logic of discovery, however, had serious limitations. For example, Bacon's logic is based on the use of the tables involving a process of exclusion and rejection. But this process may either leave open too many possibilities or none at all. Therefore, it may not lead to a necessary conclusion. To remedy to this weakness, Bacon makes a plea for giving the intellect permission at this point to try an interpretation of nature in the affirmative. That is, Bacon makes a plea for giving the intellect permission to formulate a hypothesis. For example, a hypothesis about the nature of heat. But Bacon does not really derive the hypothesis from the examination of the tables. Rather, he borrows it from one of the views on heat, which were discussed at the time. In fact, also Bacon's method provides no means to formulate hypotheses. Similarly, Descartes' logic provides no method because it is ultimately based on intuition. According to Descartes, even deduction is based on intuition, because a deduction consists of a number of simple deductions, and a simple deduction, Descartes says, is performed by intuition. Now, for intuition, there are no rules. For such reason, Descartes states that his logic cannot go so far as to teach us how to perform the actual operations of intuition and deduction, because these are the simplest and most primitive of all. For this reason, Descartes' method provides no means to formulate hypotheses. attempts to develop logics of discovery, alternative to scholastic logic, faded down in the 19th century and came to a definite end with Frege. Frege states, the question of how we arrive at the content of a judgment should be kept distinct from the other questions. Whence do we derive the justification for his assertion? Logic cannot be concerned about the former, that is the question of discovery, because it is a psychological question. This is what Frege maintains, not a logical one. Logic can be concerned only with the latter, the question of justification. For, Frege says, one cannot count the grasping of the thought as knowledge, but only the recognition of its truth. The grasping means discovery, recognition, justification. Now, according to Frege, in order to give a justification of a judgment, we must determine upon what primitive laws it is based. Then, we must deduce the judgment from those primitive laws. This will provide required justification. Because, Frege says, deduce is to make a judgment because we are cognizant of other truths as providing a justification for it. There are laws governing this kind of justification, the laws of deduction, and the goal of logic is to study these laws, the laws of deduction, because they are the laws of valid inference. On this basis, that is on the basis of this statement by Frege, mathematical logic has been developed as a logical justification and as the study of the laws of deduction. The attempt to develop mathematical logic as a logical justification, however, has not been successful. By Gödel's second incompleteness theorem, for any consistent, sufficiently strong deductive theory T, the sentence which cannot express the consistency of T cannot be demonstrated by absolutely reliable means. Therefore, mathematical logic cannot be a logic of justification, not even in the case of mathematics. Also, the attempt to develop mathematical logic as the study of the laws of deduction has not been successful. By the strong incompleteness theorem for second-order logic, there is no set of deductive rules capable of deducing all second-order logic consequences of any given set of formulas. Therefore, mathematical logic is inadequate to the study of deduction. Contrary to Frege, who considered the question of discovery a psychological question, Hilbert tries to trivialize it. On the one hand, Hilbert assumes that there is no question of discovering the axioms because the axioms can be taken quite arbitrarily. They are only subject to the condition that the application of the given axiom can never lead to a contradiction. On the other hand, Hilbert assumes that the question of discovering demonstrations of mathematical propositions from given axioms is a purely mechanical business, the decidability of a mathematical question in a finite number of operations. However, Hilbert's attempt fails because, on the one hand, by Gödel's second incompleteness theorem, it is impossible to show by absolutely reliable means that the application of the given axioms, as he says, can never lead to contradictions. On the other hand, by the undecidability theorem, for any consistent, sufficiently strong deductive theory, there is no mechanical procedure for deciding whether or not a mathematical proposition can be demonstrated from the axioms of the theory. Frege's view that the logic cannot be concerned with the question of discovery because it is a psychological question finds correspondence in Poincaré's proposal for a psychology of discovery. According to Poincaré, mathematical discovery consists in making new combinations with concepts that are already known and then in selecting those that are useful. This is the action of the unconscious mind, according to Poincaré. The unconscious mind selects useful combinations on the basis of the feeling of mathematical beauty. Once useful combinations have been selected, Poincare continues, it is necessary to verify them. This is the action of logic and of the conscious mind. Poincare's proposal for a psychology of discovery, however, is unconvincing. First, if discovery consisted, as it contains, in making new combinations with concepts that are already known, there should be some primitive concepts out of which all combinations of concepts will be made. Then, as Leibniz first suggested, it would be possible to assign characters to primitive concepts and for new characters for all other concepts by means of combinations of such characters. The resulting characters provide a universal language for mathematics, because it would be possible to express all mathematical concepts in terms of them. However, this conflicts with Tarski's undefinability theorem, by which there cannot be a theory capable of expressing all mathematical concepts, in particular the concept of being a true sensitive T. Therefore, there cannot be a universal language for mathematics. Secondly, the feeling of beauty is unreliable as a means of selection of useful combinations. For example, the feeling of beauty led Galileo to stick to Copernicus' circular orbits for planets, which contrasted with observations, rejecting Kepler's elliptical orbits, which agreed with observations, and Galileo knew about that. And similarly, the feeling of beauty led Dirac to stick to his own version of quantum electrodynamics, which made predictions that were often infinite and hence unacceptable, rejecting renormalization which led to accurate predictions. The failure of mathematical logic to provide a justification for truths already known, and the failure of the psychology of discovery to provide an account for the process of discovery suggest that a rethinking of logic is necessary. In particular, it is necessary to put a stop to the divorce of logic from method, which mathematical logic introduced. For example, Tarski stated that there's a little rational justification for combining the discussion of logic and then of methodology of empirical sciences. For mathematical logic, methodology of science and logic are two separate things. This contrasts with Aristotelian logic, which was developed by Aristotle as a tool for the method of science. Because of the divorce of logic from method, mathematical logic has had little impact on scientific research. An alternative logic paradigm is necessary if logic is to play any significant role in science. In particular, contrary to scholastic logic and mathematical logic, in the alternative logic paradigm, logic must be developed as a logical discovery and as a tool for the method of science. The claim that logic must be developed as a logical discovery is challenged, for instance, by Reno, who asks, why should the logic of discovery be revived? Now, this is my answer. With respect to logic, the logic of discovery should be revived because, by Gödel's second incompleteness theorem, mathematical logic failed to be a logical justification, and only reviving the logic of discovery by the logic may continue to have an important role. On the other hand, with respect to science, the logic of discovery should be revived because scientists, as a matter of fact, use quite a lot of heuristic tools in their everyday work. Then it may be useful to study heuristic tools systematically in order to improve current heuristic tools and to develop new ones. This means that logic must be developed as a tool for the method of science. But what is the method of science. Contemporary answers to this question involve basically two methods, which in their original form were stated in the antiquity: the analytic method and the analytic synthetic method. The analytic synthetic method includes as a part the axiomatic method. The synthetic part of the analytic synthetic method is the axiomatic method. By the way, in the modern time, the analytic part was dismissed by Hilbert practically, because he said there's no problem of discovering axiom. The axioms are arbitrary. So the analytic part was unnecessary, only the synthetic part was retained by Hilbert. So he reduced the method to the axiomatic method. Let me state briefly these two methods. First, the analytic method. The analytic method was first used by the mathematician Hippocrates of Chios and the physician Hippocrates of Samos, and was originally stated by Plato. I mean, these two scientists used it without stating it, used it in some special cases. But Plato was the first one to give a statement, a systematic statement of the method. The analytic method is the method according to which, to solve a problem, one looks for some hypothesis from which a solution to the problem can be deduced. The hypothesis is obtained from the problem and possibly other data already available by some non-deductive rule. The hypothesis need not belong to the same field as the problem, so the hypothesis can belong to any field, and must be plausible in the sense that it must be in accord with experience. The analytic method involves not only an upward movement analysis from problems to hypotheses, but also a downward movement from hypothesis to problems, because one must examine the consequences of hypotheses in order to see whether they include a solution to the problem and are in accord with experience. Therefore, the analytic method can be schematically represented as follows. Problem to solve B, upward movement analysis, and any analysis step must be followed by the reverse step. This statement of the analytic method is really a revised version of Plato's description. It differs from Plato's statement in three basic respects. First, Plato gives no indication as to how to find hypotheses to solve problems. B, Plato only asks to examine the consequences of hypotheses in order to see whether they are in accord or are not in accord with each other. This does not guarantee that they are in accord with experience, but only that they don't lead to contradictions. And C, Plato asks that knowledge be most certain and infallible, which leads him to conclude that as long as we have the body and our soul is contaminated by such an evil, we will never adequately gain the possession of what we desire, and that, we say, is truth. Thus, as Plato maintains, that we can never reach knowledge during life. My statement of the analytic method is not subject to this limitation. First, it specifies that hypotheses are found by non-deductive rules. Secondly, it asks that hypotheses be plausible, that is, in accord with experience. Thirdly, it does not ask that knowledge be most certain and infallible, but only plausible. This does not exclude that in the future, new data may emerge with which the hypothesis is not in accord. So it is not true. Now I will describe the analytic synthetic method. The analytic synthetic method was stated by Aristotle, and it is the basis of Aristotle's logic. The analytic synthetic method is the method according to which, to solve a problem of a given field, one must find premises for that field, from which a solution to the problem can be deduced. According to Aristotle, the premises are obtained from the conclusion either by syllogism or by induction. Moreover, the premises must be plausible in the sense that they must be a part of the experience. If the premises as obtained are not principles of the field in question, one must look for new premises from which the previous premises can be deduced. The new premises obtained from the previous premises either by syllogism or by induction and must be plausible, and so on, until one arrives at premises which are principles of the field in question. Then the process terminates. This is analysis. At this point, one tries to reverse the process to see whether, inverting the order of the steps followed in analysis, one may obtain a deduction of the conclusion from the principles of the field in question, which must be known to be true by absolutely reliable means. This is synthesis. The analytic synthetic method can be schematically represented as follows: conclusion, analysis, upward, then synthesis, downwards. Both in the analytic and in the analytic synthetic method, the hypotheses are obtained by means of non-deductive rules. In the case of the analytic synthetic method, this requires an explanation. As we have seen, according to Aristotle, in such method, hypotheses are obtained from the conclusion either by syllogism or by induction. What does Aristotle mean when he says that they are obtained by syllogism? Syllogism can be seen in a twofold manner, either as a means of obtaining conclusions from given premises, so as a means of justification, or as a means of obtaining premises from given conclusion, so as a means of discovery. According to a widespread view, for Aristotle, syllogism is a means of justification. This is the interpretation which has been given in the 20th century by mathematical logic, for instance. This view is based on the first 26 chapters of the first book of Prior Analytics, where Aristotle describes the morphology of syllogism. However, in chapter 27, Aristotle states, now, after describing this morphology, now it is time to tell how we will always find syllogism on any given subject and by what method we will find the premises about each thing. For, Aristotle goes on, one ought not only to investigate how syllogisms are constituted, but also to have the ability to produce them. In order to produce them, Aristotle says, we must indicate how to reach for premises concerning any problem proposed, in the case of any discipline whatsoever. That is, one must indicate for any given conclusion how to reach premises from which the conclusion can be deduced. From this, it is clear that for Aristotle, syllogism is primarily a means of discovery, specifically a means for finding premises to solve problems. For this reason, Aristotle says that while arguments are made from premises, arguments, deduction, the things with which syllogisms are concerned are problems, with solving problems. Consistently with this view, in chapters 27-31 of the first book of Prior Analytics, Aristotle describes a heuristic procedure, a non-algorithmic procedure, for finding premises to solve problems. And this procedure is described in great detail, so it's very well articulated. The medievals called this procedure inventio medi, the story of the middle term, because it is essentially a procedure for finding the middle term, syllogism given the conclusion. Middle term, because the other terms occur in the conclusion. The middle term is the only one to discover. Now, let us turn to more recent time. The originators of modern science adopted the analytic synthetic method as the method of science. Contrary to a widespread opinion, the core of the scientific revolution of the 17th century was not a revolutionary change in the scientific method with respect to Aristotle, but rather a change in the goal of science with respect to Aristotle. While for Aristotle the goal of science is to penetrate the true and intrinsic essence of natural substances, for Galileo it is only to know certain properties of natural substances, mathematical in character. Indeed, Galileo famously stated, either by speculating we seek to penetrate the true and intrinsic essence of natural substances, or we content ourselves with coming to know some of their properties, affezioni, the original term. Trying to penetrate the essence of natural substances is, Galileo says, is a not less impossible and vain undertaking with regard to closer elemental substances than with their modest celestial things. Therefore, we will content ourselves with coming to know some properties of them mathematical in character, such as location, motion, shape, size, opacity, mutability, generation, and dissolution. While we cannot know the essence of natural substances, Galileo goes on, we need not despair of our ability to come to know such properties, even with respect to the remotest bodies, just as those whose attend. But while changing the goal of science, the originators of modern science adopted the analytic synthetic method as the method of science. For example, Newton states, in natural philosophy, the inquiry of difficult things by the method of analysis, the upper part of Aristotle's method, ought ever precede the method of synthesis, the downward part of composition. Analysis consists in making experiments and observations, and in drawing general conclusions from them by induction, and admitting of no objection against the conclusions, but such as are taken from experiments or other certain truths. On the other hand, synthesis or composition consists in assuming the causes discovered by analysis and established as principle, and by them explaining the phenomena proceeding from them and proving the explanation, deduction from principles. Newton also declares that his own propositions were invented by analysis. Then he composed, that is, he wrote synthetically, what he had invented by analysis. Despite its role as the method of modern science, the analytic synthetic method has a serious disadvantage. It is incompatible with Gödel's incompleteness theorem. By Gödel's first incompleteness theorem, for any consistent, sufficiently strong principles of a given field, there are truths of that field which cannot be demonstrated from the principles. Their demonstration may require the principle of other fields. Conversely, the analytic synthetic method requires that every truth of a given field be deducible from the principle of that field. Therefore, the analytic synthetic method is compatible with Gödel's first incompleteness theorem. On the other hand, by Gödel's second incompleteness theorem, for any consistent, sufficiently strong principles, the principles cannot be known to be true by absolutely reliable means. Conversely, the analytic synthetic method requires the principle be known to be true by absolutely reliable means. Therefore, the analytic synthetic method is incompatible with Gödel's second incompleteness theorem. Since the analytic synthetic method is incompatible with Gödel's incompleteness theorems, the scientific method, unlike what Galileo and Newton claimed, cannot be identified with the analytic synthetic method. Conversely, the analytic method is compatible with Gödel's first and second incompleteness theorem. The analytic method is compatible with Gödel's first incompleteness theorem because in such method the solution to a problem is obtained from the problem and possibly other data of the already available by means of hypotheses which are not necessarily of the same field as the problem. Since Gödel's first incompleteness theorem implies that solving a problem in a certain field comprise hypotheses of other fields, Gödel's result provides evidence for the analytic method. On the other hand, the analytic method is compatible with Gödel's second incompleteness theory. In such method, the hypotheses for the solution to a problem, being only plausible, are not absolutely certain. Since Gödel's second incompleteness theorem implies that no solution to a problem can be absolutely certain, Gödel's result provides evidence for the analytic method. In view of the fact that the analytic method is the only method, at the moment known, which is compatible with Gödel's incompleteness theorem, it seems reasonable to claim that the scientific method can be identified with the analytic method. An example of use of the analytic method is the solution of Fermat's problem. Show that there are no positive solutions of the Fermat's equation for n greater than 2. Now, Ribet showed that this problem could be solved using the hypothesis of Taniyama and Shimura. Every elliptic curve over the rational numbers is modular. But this hypothesis, the hypothesis of Taniyama and Shimura, was problematic, was a internal problem that had to be solved. It was solved by Wiles and Taylor, probably, using hypotheses from various mathematical fields, and so on. Thus, the process through which Fermat's problem was solved can be schematically represented as follows. Fermat's problem, Ribet and Taniyama-Shimura hypothesis, Wiles with hypotheses from various fields, and so on. I say and so on because, of course, he used the axiom set theory, and the axiom set theory, nobody knows that they are true. It's a solved problem, of course. So, and so on. Against the claim that hypotheses for solving problems are obtained by non-deductive rules, some objections have been raised. I will consider two of them. The first objection is by Peirce. The hypotheses for solving problems are not obtained by the usual non-deductive rules, but rather by abduction. Peirce states, the surprising fact C is observed, but if they were true, C would be a matter of course, hence there is a reason to suspect that A is true. For example, Galileo observes the surprising fact C. 4 bodies change their position around Jupiter. But if A, Jupiter, and satellites were true, then C, 4 bodies change their position, would be a matter of course. Hence, Galileo concludes there is a reason to suspect that A, the hypothesis A, is true. According to Peirce, not only hypotheses for solving problems are obtained by abduction, but all ideas of science come to it by way of abduction. Thus, abduction must cover all operations by which theories and conceptions are engendered. This objection, however, is unjustified because abduction is a rule of the following form. Thus, the conclusion A already occurs as a part of the premise A, if they then C, therefore A is not really new. Peirce himself states that A cannot be abductively inferred, or if you prefer the expression, cannot be abductively conjectured until its entire content is already present in the premises. In the premise, if A was true, C would be a matter of course. And he admits that, I quote, quite new conceptions cannot be obtained from abduction. This conflicts with his previous claim that abduction kills something new, since it must cover all operations by which theories and conceptions are engendered. There is a contradiction, but Peirce wrote these things in different times. First, the first quotation from the earlier time, and this is the last formulation. Actually, new information is not generated by abduction, but rather by the process that yields the premise, if A then C, thus by a process which is prior to the application, abduction. Let us consider now Pop's objection. The hypothesis for solving problems cannot be obtained by non-deductive rules, in particular by induction, because we are not justified in inferring universal statements from singular ones, no matter how numerous, for any conclusion drawn in this way may always turn out to be false. Generally, there is no method of discovering a scientific theory. Hypotheses are not obtained through a rational procedure, but are the result of an almost poetic intuition. This is what Popper maintains. By denying that induction may be used to obtain hypotheses, and generally that any method for obtaining hypotheses exists, Popper has no other option than saying that hypotheses are the result of an almost poetic intuition. If the analytic method is the method of science, then scientific knowledge is the result of solving problems by the analytic method. When solving a problem is successful, this yields scientific knowledge. Then scientific knowledge cannot be absolutely certain, because it is based on hypotheses that can only be plausible, and plausibility does not guarantee truth or certainty. On the other hand, plausibility is the best we can achieve, because there is no special source of knowledge capable of guaranteeing absolute truth or certainty. As Plato says, human beings can only adopt the best and least refutable of human hypotheses, and embarking on it as on a raft, risk the dangers of crossing the sea of life. That knowledge cannot be absolutely certain does not mean, as the skeptics claim, that knowledge is impossible, but only that absolutely certain knowledge is impossible. As we have seen, in the analytic method, solving a problem is a potentially infinite process, so no solution is final. At any stage, the inquirer may bring up new data incompatible with the hypothesis on which the solution is based. Then, the hypothesis, while not being rejected outright, is put on a waiting list, subject to further inquiry. Even when the inquiry does not bring up incompatible data, the hypothesis remains a problem to be solved, and is solved by looking for another hypothesis, and so on. Thus, any solution is provisional. It might be objected that this does not account for the fact that mathematical results are final and forever. This objection, however, is unjustified because every solution to mathematical problems are provisionals. They are wholly good enough and lead to new and profound challenges. The analytic method suggests a sense in which this is to be understood. A solved problem is still not completely solved, since no hypothesis is absolutely justified. Any hypothesis which provides a solution to a problem is liable to be replaced with another hypothesis when new data emerge. As we have seen, in the analytic method, hypotheses are found by means of non-deductive rules. Of course, finding a hypothesis is not a sufficient condition for discovery, because discovery requires hypothesis to be plausible. Nevertheless, finding a hypothesis is a necessary condition for discovery, and in that sense, one may say that non-deductive rules are rules of discovery. Rules of discovery are not a closed set, given once for all, but rather an open set, which can also be extended as research goes on. Each such extension is a development of the analytic method, which rules add new, non-deductive rules are added. I will now give some examples of rules of discovery and their use in solving some very elementary problems. Elementary because I want the solution to be short. Such examples are to be made in the spirit of Polya. Polya writes, I cannot tell the true story how the discovery did happen, because nobody really knows that. Yet, I shall try to make up a likely story how the discovery could have happened. I shall try to emphasize the inferences that led to it. that nobody really knows the true story how the discovery did happen is due to the fact that discoveries generally don't reveal their way to discovery. They do so not because at the start the cards suggest they conceal it with a sort of pernicious cunning. They do so rather because either they are not fully aware of how they arrived at their discoveries, or they feel uneasy to reveal that their way of discovery was not deductive and so it's dirty in a sense. First example. First example involves induction, but a special case of induction. Induction from a single case, not from many cases. What is induction from a single case? Is an inference of the following form. A thing A of a certain kind, A, capital A, is B, as property B. Therefore, all things of kind A are B. So it is an inference by the following rule. First premise, A is A. Second premise, A is of kind B. Therefore, for all x, if x is A, then x is B. An example of use of this rule, induction from a single case, is the Pythagorean's discovery that the three angles of a triangle are equal to two right angles. The Pythagoreans consider a specific triangle, PQR, and through P, they drew a line ST parallel to QR. Then, in the well-known way, they showed that the sum of the angles of the triangle PQR is two right angles. From this figure, they conclude by induction from single case that it holds for any triangle. Then the argument pattern is as follows. Let A be the triangle PQR, let AX means X is a triangle, and let BX means the three angles of X are equal to two right angles. Then we have AA is a triangle, and AB, the triangles of X are equal to 2. Then from AA and BA, by induction of the single case, we conclude that all triangles have this property. Second example. Let this notation means A is to B as C is to D. Let me consider now this analogical rule of inference. Proportional analogy by permutation of the middles. What is this inference? It's an inference of this kind. If A is to B as C is to D, from this we can conclude that A is to C as B is to D. So, proportional analogy by permutation of the middles is an inference of this form, by this rule. An example of use of this rule is Hippocrates of Chios' discovery of the hypothesis that circles are as the squares or the diameters. For a given circle PQ, let RS be the square on its diameter, circumscribed to the circle. And similarly for the other circle, given circle V, let WX be the square of the diameter and so on. Then, circle PQ is to its diameter, S is to its square, S, and the circle QV is to its square, WX. From this, by proportional analogy, Hippocrates of Chios infers that the circle PQ is to circle UV as the square RS is to the square WX. Thus, the argument pattern used by Hippocrates of Chios in discovery is the following. Let's see, I'm just applying the rule. Third example. Let T arrow S stand for the elements of a domain T called the target domain are to be considered as if they were elements of a domain S called source domain. Metaphor is an inference of the following form. If if A and the elements of S have a certain property, then also the elements of T have that property. You can see from the formula, right? This is metaphor, metaphorical inference. Now let me give an example. Again, I will quote the Pythagoreans. The Pythagoreans' discovery of the hypothesis 1 plus n is formula for the first n natural numbers. Now, from the following diagram you can see there, by metaphor, the Pythagoreans conclude the result. Why? Look, let T be the domain of positive integers, and let S be the domain of triangular figured numbers, that is, geometric figures of the following form. Now, what does it mean? T, arrow, S means let's consider numbers as if they were figured numbers, geometric forms, right? Then n is a number. Let AX means the formula we want to discover. If X is a triangular figured number, then this formula, see, you remember, the diagram shows that this works. Then we are just using metaphor. By metaphor, from the fact that numbers can be considered as if they were geometric forms, and the fact that geometric forms satisfy this rule, we infer that also numbers satisfy this rule. You see, this is a metaphor. The Pythagoreans did not really prove that numbers are like that. They only proved that triangular numbers, that is, geometric figures, have this property. But then they inferred that also numbers have that property. To conclude, the possibility of a logical discovery is often denied by saying that there are no rules, I quote, ample, by which hypotheses or theories can be mechanically derived or inferred from empirical data. The transition from data to theory requires creative imagination. The discovery of important, fruitful mathematical theorems, like the discovery of important, fruitful theories in empirical science, requires inventive ingenuity. It calls for imaginative, insightful guessing. Now, these claims are based on the following alternative. Either there are rules by which hypotheses or theories can be mechanically derived or inferred from empirical data, or the discovery of hypotheses or theories calls for insightful guessing, thus induction. Intuition. Sorry. The alternative is unjustified, because between the determinism of mechanical rules and the inscrutability of intuition, there is an intermediate region inhabited by heuristic procedures. The first form of the alternative, the mechanical one, corresponds to Bacon's assumption that in forming axioms, a form of induction different from that in use must be taught. Through it, the mind is from the very outset not left to itself, but constantly guided, so that everything proceeds, as it were, mechanically. Being mechanical, this form of induction is such as not to leave much to the acuteness and strength of talents, but more or less to equalize talents and intellects. Very democratic. But Bacon's assumption is unjustified. The purpose of a logical discovery is not to dispense with the need for intelligence by use of mechanical rules, but rather to expand natural intelligence, providing it with tools capable of guiding it, though not infallibly. Such an expansion is provided by heuristic procedures, which, rather than constantly guiding the mind so that everything proceeds mechanically, give the mind tools for finding hypotheses and theories. The latter then can be obtained from the data by means of non-mechanical, non-deductive rules, without need to call for imaginative insight. Yes?